So for number 11, it says limit as x approaches 0 of e to the x minus 1 all over x. So this is also indeterminate form, 0 over 0. But then in this case, you can't use anything else like conjugate simplification or other things. So you might be wondering what you need to do. So in these cases, you can also do this one method. So set f of x as e to the x, right? Okay. So, and then you're going to say f prime of 0. You're going to use the derivatives in terms of limits, the definition of the derivative in limits to solve this. So f prime 0 is equal to f of x, or limit x approaches 0 of f of x minus f of 0 all over x minus 0, right? So in the context of the problem, we're going to have limit as x approaches 0 of e to the x minus e to the x to the power e to the x when x is 0 is going to be 1 all over x, right? So we can kind of see that f prime 0 is equal to limit x approaches 0 e to the x minus 1 over x, which is what we're trying to get, right? So in this case, we can just get f prime 0 of f of x, and that will be the limit or the answer that we're looking for. So f prime 0 is going to be f of x is equal to e to the x, so f prime 0 is going to be 1. So our answer is actually going to be 1. Okay. Okay, here is number 12. So limit of x approaches 0 of secant x minus 1 all over tangent squared x. For this one, we're going to use a trig identity. So we have 1 plus tangent squared x equals secant squared x, right? So tangent squared x can be written as secant squared x minus 1, right? So we're going to rewrite this. So limit as x approaches 0 of secant squared x minus 1 all over secant x minus 1. Okay, so that means limit as x approaches 0. Again, I forgot to do this, but make sure to plug it in. So we get 1 minus 1 all over 0, or 0 over 0. Okay, so we're going to say secant x minus 1 times secant x plus 1 and then secant x minus 1, right? And then we can cancel these two out, or limit of x minus 0, and limit as x approaches 0, secant x plus 1 over 1. Secant 0 is 1, and a plus 1 is going to be equal to 2, right? So that means we have an answer of 1 over 2. Okay, that's our answer for number 12. And then number 13, we have limit as x approaches 0, and then 6x squared, and then 5x to the third. So for this one, I'm going to try to factor out. Obviously, we get 0 over 0, right? So let's try to factor this out. So x squared times 6x all over 5, all over 5 and 5x, no, I made a mistake here, times x squared. Let's cancel all x squared, so we get limit as x over 0, x to the 0, 6 over 0, let's not do this, 6 over 5x, and then we get 6 over 0, or infinity, as our answer. Okay, and now we're going to move on to number 14. Okay, right here is a piecewise function, so let's dive into part A. So limit as x approaches 1 of f of x equals. So obviously, since we have a piecewise function, we need to evaluate both the left and right limit as x approaches 1, right? So let's do limit as x approaches 1 from the right, f of x would definitely be here, right? Some values bigger than 1, yeah. So that would be limit x approaches 1 plus ln x plus 2. So ln 1 is essentially 0, right? So 0 plus 2, we get 2. And a limit as x approaches, limit as x approaches 1 from the left. F of x would be limit as x approaches 1 from the left of 2. Or we get 2 as our answer. This means that limit x approaches 1 from the right, f of x equals limit limit as x approaches 1 would essentially be 2. This is our answer. And then going off to part B, so from 3 plus, so some values that are greater than 3. So let's see. Approaching from values greater than 3, we would get limit x 3 plus 4x, right? Or we just plug in 3 to 4x, or 12. So answer. And then part C, 3 minus. So approaching from values a little bit less than 3. So that means that we're going to do the second condition, right? We're doing the second condition. X approaches 3 from the left, and then ln x plus 2, right? And then we do ln 3, right, plus 2, which is definitely not equal to 12. Okay, that's what we get. And then moving on, is the function f of x continuous at x equals 1, and then what about x equals 2? So what it says right here is that when x is equal to 1, which basically we're going to plug, that means we're going to plug 1 into ln x, right? Ln x plus 2. So the conditions mentioned for continuity, function value needs to exist, and the function value, or the limit value needs to exist, and the limit value and the function value has to equal to one another. So for our function value, we're going to plug in 1 to the second part, because this is when x is greater than or equal to 1. So ln x plus 2, and then plug in 1, we get, again, 2, right? And our limit was 2, so which is equal to limit x. Okay, so that means that at x equals 1, f of x is continuous. At x equals 1, f of x is continuous. And then at x equals 3, we don't really know, right? Because we actually, the x equals 3 part is going to be wrong, right? It's not going to be continuous, because part B and C show that the limit does not exist, because the left and right limit are not equal to each other. So at x equals 3, that function is not continuous, as the limit d and e does not exist, right? And then it's always good to write a conclusion. So at x equals 1, f of x is continuous as the limit value exists at x equals 1 as equal to 2, I guess. Like the limit value at x equals 1 is equal to 2, which is also equal to the function value at x equals 1. But then at x equals 3, the function is not continuous, as the limit at x equals 3 is does not exist. Yeah. Okay, and then part E. If you plug in e to f of x, what happens? This is basically like as x approaches e, and then e is a value around like 2.7, so it's definitely in the second category again. So let's plug in e to the second category. So limit x approaches e, ln x plus 2, right? And then if you plug in e to ln x, we get 1, right? And then 1 plus 2 equals 3. Alright, okay. And let's now move on to the next question. So 15. This will be our last part of limits. So we're gonna look at the graph and try to answer these questions. So approaching -2 from the right side. So negative 2 from the right side, we would get 4, right? Like we're approaching it from the right, like a little bit bigger than negative 2, right? So we get 4. And then approaching negative 2 from the left, right? A little bit less, little bit less, right? But then we're approaching negative 2, so that means we are going to get 2, right? Okay, and then moving on, so x is approaching 3 from the right, right? From the right side, so like approaching from like 3.1111 or 5, right? And then approaching 3 from the left, so approaching like 2.99999, and then reaching 3, we're going to equal 4, right? So 4 again. Okay, and as x is approaching 5 from the right side, so on the right, like a little bit bigger than 5, so like 5.5, 5.1111, like that much. Obviously that means that we're going to have negative infinity right here, right? Negative infinity. Okay, and then since we have an asymptote, right, we can see that it's always going to be approaching 5 but never quite there, so it's going to keep on going down until it reaches infinity. Okay, so as x approaches 5 from the right, we're going to be approaching negative infinity, right? Like a little bit greater than 5, like 5.1, 5.00001, but then it's never really going to reach 5, right? Because we have an asymptote, so it's going to keep on going down into negative infinity. That's why we have negative infinity right here, and I'm approaching 5 from the left. From the left, we're like approaching from 4.9999999, and then we have an asymptote here, but then the circle is not filled, so it's not really like a function value, but then our limit from the left side is still approaching 13, right? And then finally, limit as x approaches 5 of f of x. Since the left and right limit are not equal, we're going to have dne for this one. That's it.